이게 텀이 길었나?
프리뷰가 지금 돼 있고 스타트 스트리밍 안 눌렀거든요.
눌러주세요. 그거 왜 계속 확인?
그래서 이제 나가요.
이제 나가야 돼.
됐어, 이제 됐어요. 이제
오케이
나갑니다.
오케이. 웨비나 시작 4분 전입니다. 마이크 테스트 중입니다. 하나 둘 셋.
지나가는 행인이.
저희 웨비나 4분 뒤에 시작하겠습니다. 잠시 후에 만날게요. 시선 처리가 지금 빅터 쪽으로 되어 있죠. 오케이. 잠깐만 빠졌다가 소리 잠깐만 꺼주실래요, 상윤님?
마이크?
아니야. 네, 안녕하세요. 유니티 코리아의 석세스 어드바이저 박주연입니다. 저희 지금 5번째 웨비나 이제 시작을 할 건데요. 지난 5월에는 유나이트 때 저희가 현장에서 만나 뵈어서 웨비나 진행을 못했고, 이번 세션으로 다시 또 6월 달에 저희가 그 다츠 세션을 하고 7월에 HDRP 세션으로 다시 돌아왔습니다. 저희가 유나이트 때 저희 빅터님께서 HDRP 세션을 진행을 해주셨었는데요. 그때 저희가 관련된 피드백을 워낙 좋게 받기도 했고, 저희 유니티가 앞으로 계속적으로 선보일 고퀄리티의 그래픽 관련된 렌더링 파이프 관련된 내용이라 저희가 심화 내용으로 다시 한번 구성을 했습니다. 그래서 이번 웨비나는 조금 특이하게 오늘 진행한 거에 이어서 다음 달에 빅터님이 또 한 번 그 내용을 이어서 진행을 해주실 거고요. 그래서 조금 그러니까 유나이트 때보다 조금 더 심도 깊은 내용으로 연결이 된다고 생각을 해주시면 될 것 같습니다. 그럼 본격적으로 바로 세션으로 넘어갈 거고요. 오늘 세션은 영어로 진행이 돼요. 근데 영어 내용에 대해서 좀 부담을 가지실 수는 있는데 실제적으로는 저희가 스텝 바이 스텝으로 저희가 실제 툴을 다루는 내용들이 많아서 이렇게 영어에 대한 부담은 크게 느끼시지 않고 편안하게 들으실 수 있는 세션이 될 것 같고요. 나중에 저희가 이번 달과 다음 달 진행한 영상을 모아서 한글 자막을 넣은 영상을 별도로 또 공개를 할 예정이라 이번 좀 웨비나 참석이 어려우신 분들은 그때 기회를 활용해 주시면 될 것 같습니다. 그럼 오늘 세션을 담당해 주실 빅터를 소개하겠습니다. 자기소개 부탁드릴게요.
네, 반갑습니다. 유니티 코리아 필드 엔지니어 빅터입니다.
네, 저희 빅터님이 원래 한국말을 못하시는 건 아닌데 아무래도 한국분이 아니시기 때문에 영어로 전달하시는 게 조금 더 표현력이나 좀 깊이 있는 설명이 가능해서 이번 세션은 영어로 진행되는 점 다시 한번 양해 말씀 부탁드리고요. 그럼 빅터 본격적으로 세션 진행해 볼까요?
네.
네.
저희 그 PPT 갖고 있나요?
네.
So hello guys. So I did this presentation at Unite, but I heard a lot of feedback that it's actually better I do it in English. So I'm gonna do it in English this time. It's basically like we are going to go over the more how HDRP renders a frame. We'll start from when it's very simple and go into like progressively more complex frames. So you can see we will start with HDRP in one of its simplest configurations. So it's just a deferred renderer in that case. The next we'll add alpha tested material, global illumination, and some screen space pre-lighting calculations, so that we have a level that's similar to a Unity legacy pipeline. And then we'll add forward materials. This will introduce us to the forward deferred hybrid architecture that HDRP has. We'll also add some post-processing effects. For this webinar, we'll just go over these 3 frames in detail. So we'll do it slowly and in detail. So the tool we'll use, use Insight Graphics to take GPU captures. As a fact, RenderDoc also works very well, but because our computer uses NVIDIA graphics card, so we're using Insight. We'll also take a break. Those are the things we'll talk about next session, right? So next session we'll talk about decal, lightless building, feature categorization, and SSS, so subsurface scattering. We will not talk about a lot of the really cool features. So there's no area lighting, volumetric lighting, no refraction, no advanced shaders like hair, eyes. There's no talk about RTX. So the talk is focused on a very detailed look on the most basic part of HDRP. Our version is 19.1. The HDRP version is 5.7.2. We're on linear color space. Yeah, we're on DirectX 11. DirectX 12 would be faster, but 11 probably profiles better. So when we build with 11, the GPU capture is actually gonna be more easy to understand. That's why we use DirectX 11. So we're going through 3 frames. This is frame number 1. The structure of this is we will go through the PowerPoint to go over the key concepts, and then next we will actually do the GPU capture and check out how it's rendered in real life. The frame 1, almost everything is turned off in our HD render pipeline asset. You have a choice to do deferred only, forward only, or forward deferred hybrid. In this, we just do deferred. And we render this opaque object with shadow map under just one directional light. And we also have exposure control. This is just so that we don't render the frame way too bright so that it looks weird. Exposure control basically just darkens your final rendered frame when it's too bright and make it brighter if it's too dark. We have a bore. So in the scene, there is a bore that is high metallic and low in smoothness, and a bore that's high in smoothness and low in metallic. So this is just to help us understand how the physically place rendering works. Anyway, so actually let's look at the scene to better visualize our setup. So here is our scene. So when you're setting up HDRP, the biggest, the most global setting that you can get. So if you go to project settings, and then graphics, here is where you tell Unity we are going to use this setting for my rendering pipeline. So this is just a scriptable object where you specify your settings that you want for your rendering pipeline, and this is a project-wide setting. So your whole player is going to use this setting. It helps especially with shader stripping and other things. When HDRP knows you're not using something on the project scale, it helps it optimize and strip away unnecessary things. So in this case, we're using asset number 1. And you can see most of the thing is turned off. It's gray. Gray means turned off, not tick means turned off. So the only thing that's tick is just opaque object. So we're drawing opaque object. We are having shadows. There is exposure control, and that's it. It's a very simple setup. Now, besides settings, the second thing that's on the scene level, you have volumes. In 2019.1, starting with that, we no longer use post-processing stack. The post-processing volume and HDRP volume gets unified into just this volume component. So this is a scene setting, and these volumes can blend. So if you have a volume, you can make it a global volume, in which case this volume will be effective across the whole scene. Or you could make it a not global volume, then you need to define the bound, and depending on the camera location relative to that volume, it would just blend. If you're close to the volume, you would use that volume's setting for your camera. But here we are just using a global volume for simplicity. We have very simple setups, just saying we have cascade shadowing. And if you look at the scene, it's also very simple. We don't have any GI, and if you look at the balls, so here is our material with a with a high metallic low smoothness. Here's our material with a high smoothness, low metallic. Yeah. Okay. So this is the scene setup. Okay. Let's go through the theory of the scene. So this will be a very standard deferred rendering process. We'll have a GBuffer Pass, then we'll render shadow maps, and using the GBuffer and the shadow maps, we will do a deferred lighting pass. So the first thing is the GBuffer Pass. GBuffer encodes the information of the material needed for lighting calculation. So to understand the GBuffer, it helps to first look at the BRDF we use in the lighting calculation, and then find out what these BRDF needs. So then these needed data will decide what gets encoded into the GBuffer. So just like our legacy rendering pipeline, the direct lighting is composed of diffuse and specular terms. Diffuse is when the surface absorbs the light. It bounces a little bit in the surface and then come back. And specular is when the light just like bounce straight away from the surface, not absorbed by the surface. So specular has a very high sensitivity to your view direction, but diffuse has a lesser sensitivity to your view direction. Now, the diffuse term, let's talk about the diffuse term. Our diffuse term uses modified Burley's diffuse. So that the Burley's diffuse was introduced by Disney. It's a new version than, let's say, Lambert diffuse. So we have the diffuse color, like usual, but we also have some Fresnel term. So this really is taking into account the normal versus the light direction, and it's kind of depending on the normal and light direction. It's either F, it goes from F to 1. And here it depends on the normal and view direction. It also goes from F to 1. For those interested, the reason we have this and that is in order so that the BRDF is the same when the light direction and view direction are switched. There is such a rule in physics. The value of F is determined by roughness. It roughly goes from 0.5 to a number that's quite bigger than 1. Actually, it goes from 0.5 to 2.5. So like the edge lighting, it's depending if it's smooth or not. The edge is darker than usual or brighter than usual, which it's pretty interesting. There isn't an actual very strict physics about it. I think in Disney's paper they said it just looks very pleasant and kind of has a physical meaning. So we don't need to think about it too much. Anyways, right. So let's look at this again. Just diffuse color with some normal lighting angle term and some normal view direction angle term. Anyways, like the equation itself is not important, but what is important is we need these for calculating. So what we need is diffuse color, roughness, normal. Yeah, these are the stuff we need. View direction we will get when we actually do deferred lighting, so that's not important. For specular, we are using Smith joint GGX. Smith joint GGX. This is one of the variant of Cook-Torrance specular term. We'll not go into detail, but let's just look at what this needs, right? So what it needs, just like diffuse, it needs roughness and normal of the surface, but it also needs F0. So what F0 means is Fresnel at 0 degree. So what is that? It means specular reflectance at normal incidence. So actually just look at this picture, right? So here is your surface. The light, a white light with 111 in RGB value goes into your surface, and if you look at what is reflected back, what the color that's reflected back is your F0. And what is important here is it's only the reflected light. It should be the specular term, right? So it's when you shoot the ray into the surface, some is absorbed and then re-emitted. We do not count those. We only count the one that's absorbed and bounce back. So specular, that's why it says specular reflectance, right? It's not a diffuse reflectance. And if you look at the physical surfaces, if it's non-metallic, it's not tinted. So it's a KKK for some K less than 1. If it's a metallic surface, it is tinted. So it's going to be XYZ, where XYZ could be different. So, you know, like when you're making a material in Unity, right? The artist will specify a albedo map, metallic, smoothness, normal. These are the things specified by artists. These are the artist-friendly data. But as we mentioned before, our BRDF needs diffuse color, F0, roughness, more normal. So these are our more physically based parameters, right? So we need some way to transform the artist-based data into physical-based data. And let's just look at those one by one. Normal is the same, right? We just like copy it. Smoothness is kind of different from roughness. There is also some other details. There's actually perceptual roughness and roughness, but we're not going to detail here. Just smoothness is like the opposite of roughness, right? So there is some equations that helps us understand it. But albedo, metal, diffuse color, F0, these are like more mysterious what they do, right? So if you look into the shaders of HDRP, there is a function that compute diffuse color from albedo and metallic, which just lerps between 0 and base color based on metallic. And there is a term that calculates F0, which just lerps from base color to this dielectric F0 term, which is basically just 0.04, 0.04, 0.04, and based on metallics. But basically, the most important thing to remember is if it's a very metallic surface, F0 is close to your albedo map. Your albedo map mainly goes into your specular lighting. If it's not metallic, the diffuse color is close to your albedo map. So your albedo map's color is mainly going into the diffuse lighting calculations. So all these basically just translates into our GBuffer layout. So the 0 GBuffer has RGB diffuse color. The F0 RGB is in GBuffer number 2. We have the encoded normal in the GBuffer number 1. And we also have roughness, right? Here it's the perceptual roughness, if you know very much about PPR. There are other things. We'll skip those. For the normal, there is a encoding that we do to improve the precision of the normal in our GBuffer. So, you know, like normal is a unit vector in 3D space. So it's basically maps into a sphere. You can make the sphere into an octahedron, and the octahedron can be folded into a square. In that case, you reduce from 3 dimensions to 2 dimensions. Then you can actually use the 24 bits of data into encoding two 12 bits numbers, right? This will give us high precision with the same memory footprint. So yeah, so that is the GBuffer pass. Now, shadow map is just cascaded shadow mapping, just like a built-in pipeline. So let's look at deferred lighting now. The first thing to note, unlike in built-in pipeline, we use the sensor buffer extensively in HDRP. So here you can see that our scene where there is something, there is some material, right? You would write to stencil buffer a mask, says, hey, there is something to draw. I should receive some lighting. And during deferred lighting pass, we only do lighting calculation on those pixels. And the pixels that we do not do lighting calculation on, we will only on them do a skybox pass. So this not only reduces the amount of deferred lighting we have to do, it also reduces the amount of sky painting that we have to do as well. So it's pretty good. And deferred lighting, when we because like actual deferred lighting in HDRP in usual settings is very fast compared to this, because we turned off all the optimizations. When we turn off all the optimizations, it's very simple. Basically, you just find out all the lights, right? So there is point lights, spotlights, whatever lights. Just gather all of them and sort them by the light type, and then upload them into the GPU from the CPU, and they will sit in a structured buffer. So this is HLSL. You will see there's directional lights data is in one structured buffer, and there is also light data which has all the punctual lights, area lights, image-based lights, all that. And basically all we do is just we just loop through each light and ask each light to contribute illumination to our fragment, right? There isn't anything special about that. But of course, this is an improvement from Legacy. Legacy, we do a lot of additional blending. So how are we on timing? Okay, cool. So we're going through 3 frames, right? So half an hour each is good. Okay. So we are now looking at NVIDIA captures. We already have our scene. Oh, actually, let's look at our scene a little bit. Oh, we can't see it. Okay, in that case, our scene in the end looks a bit like this, right? This is the scene that we're rendering. This is the scene we're rendering, right? 2 boards, some views, some boxes, pretty amazing graphic. Not so these green stuff means that these orange stuff means we're uploading stuff. So uploading meshes, textures, those uploads. Now we're clearing the buffers. So the first interesting thing here is when we're drawing to GBuffer. So we are drawing to GBuffer, and here you can see we are mainly drawing to 3 GBuffers. Color 0, this is the first GBuffer. These are the diffuse colors, and this is weird because it is encoded normal, because normal is encoded. It's not really continuous. It looks kind of weird. And this is the F0. So you can see in F0 only the ball is red, because that ball is our metallic ball. Everything else is not very metallic. So as we said, right, if you have a metallic surface, most of your albedo map goes into specular lighting, and specular lighting's color comes from F0, so it's here. In contrast, you can see the diffuse color. The metallic bore is basically black. It has no illuminations in terms of diffuse lighting, and the non-metallic bore has a very red color, and so does most other things. Most things are like insulators. Yeah. So this is the GBuffer structure, right? Diffuse color, normal, F0. Now we finished our GBuffer Pass. What comes next? What comes next is Compute Shader. So if you look at the marker that we have here, it's copying out the depth buffer and making a map out of that. We often use special calculations, screen space calculations, where we need to know about the geometry of the scene. So after we do our GBuffer Pass, where we know all the normal or the depth information is ready, and normal information is ready, we will copy it out so that we can use it in the later passes. Anyway, so this is basically getting the depth buffer and generating a map chain. We need a map chain from the depth buffer in case we want a lower resolution version of the depth buffer. Then we can get very large scale information with very little texture fetches, right? So we do a map chain, this is just getting some depth geometry out of the scene in case we need it. But in this case, we don't need it. We don't use it. So let's just skip over this. Now we are rendering shadows. So we are having 3 shadow cascades. This is basically the same as how we're doing it in built-in rendering pipeline. There's 3 shadow maps. Each one is close to the camera, one is far away from the camera. We allocate more texture memory to find out to encode the shadowing data close to the camera, because stuff close to the camera has greater actual screen space, actual screen size, right? So things close to the camera is bigger on your screen, so they are more important. So we want higher resolution shadows for them. That's why we have some extra texture space to encode shadow data for objects close to the camera. Anyways, so here we go, cascaded shadow map, and then if you can see, like, this is like how much the GPU is using its resource, this timeline. The biggest chunk is used here. This is, if you look at this, green as we said is clearing, orange is upload, these purple markers are compute shaders, this blue marker is fragment shader. So we have this very time-consuming fragment shading cost. That is actually just us drawing a full screen quad. So here we draw a full screen quad, and if you look at what the pixel shade is doing, it's using this GBuffer. It's also using the shadow map and some other stuff to basically just draw for each fragment the lighting calculation from the directional light, right? So here in practice we have just one directional light. Unity knows there's one directional light, uploads the information about that directional light into a structure buffer. The deferred lighting shader just queries that structure buffer. Hey, there's just one directional light. Let's just illuminate this fragment with that directional light based on what we know about that fragment. And finally, there is post-processing. The post-processing basically is just doing some exposure calculations. So it's summarizing how bright the scene is, so that on the next frame, when we do this again, when we do the deferred lighting again, one of the input here, you can see this green texture, right? This is the exposure texture. It shows the last frame's exposure. With that, you can make the whole rendered thing darker or brighter so that it looks correct to the eyes. And we have a final blit, and it's all done. So frame 1, very standard deferred rendering. Frame 2, let's go to frame 2. Yes, half an hour, excellent. So in frame 2, we are doing a lot of global illumination stuff. So we added Shadowmask. We also have Shadowmask inbuilt in. We added screen space reflections, screen space ambient occlusion. We added these effects. We need to add it both in the project setting and the scene local settings, right? So here we have the setting asset, and we also have the volume component. Both needs to be set up. And also we need to set up in the lighting window that communicates with the light map baking system. So we also need to tell that to bake the correct lighting information. So we are telling them, hey, we need a baked global illumination in Shadowmask mode. And in terms of the scene, we added two things. The first thing we added is grass. What is so special about grass? Grass is a alpha tested material. So it uses a texture to determine if your fragments should be discarded or not. So that you can use the texture to specify the shape of the grass. we also have a very smooth ball. The ball is basically acting as a mirror here. We also have light probes, reflection probes, so that GI works properly. Okay, so let's look at the setup here. Frame number 2. Yeah, the graphics is vastly improved, of course. So there's two things we should look at, right? So here you have some grass. Let's click the grass and come out grass. Okay, so the grass is this guy. You can see there's a alpha clipping, right? So we enabled, so most of the shaders here is using the lit shader. This is the basic shader in HDRP. If you want to do more advanced stuff, you can go with the HDRP shader graph, or you can make your own HDRP shader. That's reasonably complicated, but it's doable. But to start off, most people just use lit shader. It's like the standard shader in Legacy. And here, most of the other lit shaders, we don't have this, right? So there's an alpha clipping option. We turn it on, and here's a threshold, right? So if you change the threshold to 0, it would do no alpha clipping, right? So this is the actual shape of the mesh, but depending on the alpha texture, you can see, right? It's you can adjust the grass. Okay, next is the mirror-like ball. Let's go to the mirror-like ball. Here we go. Mirror-like ball. It's a reflective material, and what is special about that is we have a receive SSR, so that we ask Unity to do reflection calculations, screen space reflection calculation. Even if it doesn't receive it, it's still going to get some reflections from reflection probes, of course. But what is making it very shiny is, one, it's receiving SSR, so that, but also the most important reason is probably because it has an extremely high smoothness value, right? Yeah, that very smooth object. So, right, okay, so this is the setup. Now let's look at the theory. Okay. So the first thing we need to think about is how do we deal with the alpha tested materials? Usually alpha tested materials problem is that if you alpha test, then you cannot early Z. It's a very complicated reason, and we will not go into detail about it, but it's a well-known fact. So it's because we can't do early Z, things that actually is not going to be painted will still do fragment calculations. So we were doing some useless fragment shading. The solution is that, okay, we accept that we can't early Z, but we are going to do a depth prepass. So we do a deep depth prepass where we only draw to the depth buffer. And when we are doing the depth prepass, we use alpha test. Now, this is fine. In the depth prepass, we can't early Z, so we are doing useless fragment shading. But the useless fragment shading is really cheap because we are doing basically nothing, right? We just draw the depth value. Now, of course, we will have to eventually do the draw to GBuffer. But when we're drawing to GBuffer, we do not enable alpha test. We use z test equal. So we use the depth buffer to tell us if that grass should be drawn into GBuffer or not. So here is this illustrated in pictures. The first thing we do is a depth prepass with alpha tested material. The second thing we do is we GBuffer pass with non-alpha tested material. And then finally, we draw with alpha tested material, but with no alpha testing. Instead, we use that test equal. And this works because we have done the depth prepass. So this is alpha test material. So this is important because it explains why you have this depth prepass with some stuff, right? The next thing we need to look at is global illuminations. So before we do the deferred lighting pass, you remember the huge whole screen quad fragment shader. We use a lot of extra data so that we can do more complex BRDF calculations. Let's check all those extra data that we generate out one by one. The first thing we have is Shadowmask. So if you look at the Unity project, we already baked some light maps and shadow mask from the scene at build time. So before, not at runtime, right? So when in the Unity editor, we already baked these data. So this is encoding like the static meshes in the scene if they are occluded by other static meshes in the scene. And this is stored in GBuffer 4. Next up, we have Indirect Diffuse. So this is stored in GBuffer 3, and it looks like this. So this is using the baked directional light map. So when you bake in Shadowmask mode, this and that are the two light maps that's showing the indirect diffuse lighting in the scene. One is encoding the dominant light direction, one is encoding the brightness. Now, we also have light probes used for dynamic meshes. Now, at the GBuffer Pass, if you are a static mesh, you would check from your light probe. And if you're a static mesh, you check from your light map what the indirect diffuse input is, and then you would encode into the GBuffer your indirect diffuse lighting. If you are a dynamic mesh, then you would check from the light probe and occlusion probe about these things. And these information are stored in GBuffer 3. So this is basically just saying it's storing the fragments, what indirect diffuse light the fragment is receiving. So these are coming from global illumination, baked global illumination systems. Next we have reflection. Reflection is the same as indirect specular. So indirect diffuse, indirect specular. Now there is, first off, we have an environment map. It captures light coming from each direction in sky. Looking at it the most simply, it's a cube map that encodes this information. So it's like a camera shooting in every direction, but it's a little bit more complicated than that. There is some extra data structure that encodes some extra things about this. We are using split sum approximation. This is a very popular method in real-time rendering nowadays. Similarly, we have indirect specular coming from baked reflection probes. This is not the sky, but just the static meshes in the scene. And again, it's using split sum approximation. And there's also consideration of blending or projection, which we're not going to talk about. So reflection probe is like a 360-degree thing, but there is also a planar reflection probe which you can use, but we are not using it in here, so we're skipping that concept as well. And finally, there is a screen space reflection texture. So we basically shoot ray from the camera to each pixel in the depth buffer, and we reflect that light, and then match that reflected ray to see if it hits some other pixel in depth buffer. Here we only know about the depth buffer, so it's a little bit it's a screen space technique. So if it's some information that the GBuffer doesn't know about, then we can't retrieve that information. So we can possibly not find out. So like screen space reflection may tell us what the reflected ray is hitting, but when it cannot, we will try to ask if the reflection probe can tell us, and if the reflection probe cannot tell us, we'll try to find information from the skybox. Finally, there is ambient occlusion, right? Okay. So ambient occlusion, we are doing a screen space ambient occlusion, where we are trying to find out how much each pixel is surrounded by solid instead of air. So if a pixel has a lot of neighbors which is solid, then those solid are going to block any indirect light trying to travel into that pixel, right? So the more the pixel is surrounded by solid, the less indirect light rate it's able to get. So this will affect indirect diffuse and indirect specular by darkening the illumination. Now, in our talk, occlusion only comes from SSAO pass because all of the materials that we have has not set any artist-provided occlusion data, but it is possible for artists to set occlusion data using the G channel of the mask map and the bent normal map. It's a very complicated process, but looking at the high level, we just do our best to use the darker of the two sources to appropriately darken the indirect diffuse and indirect specular. Now, there are two exceptions. You know, like we said that direct lighting should not care about ambient occlusion, but there is two ways ambient occlusion can affect direct lighting. So the first is if you enable direct lighting strength, this option in your ambient occlusion setting in your HDRP volume, then it enables SSAO to capture some direct occlusion detail. So if you set direct lighting strength to a non-zero value, occlusion, your SSAO will partly darken your direct lighting. And one thing that's very important to note is this only takes data from SSAO, not baked AO data. So direct lighting strength allows the artist to take some darkening from SSAO into their scene to darken direct lighting. On the other hand, right, you can also add this micro shadows option in your post-processing volume. Now, micro shadows is taking data from baked AO data, right? So those are the your G channel in the mask map or your bent normal map. So these occlusion data will affect direct lighting if you turn on micro shadows, and we are not using SSAO. What this is doing basically, it's enable micro shadowing. So enabling micro shadowing means your AO texture not only influences indirect light reception, but also influence self-shadowing during lighting calculations. So the theory is here. Your amount of ambient occlusion dictates how big this cone is, and you also know the normal direction, either from the normal map or the bent normal map. In that case, you also know the light direction. So the light, if it's outside of this cone, the direct lighting could actually be self-shadow. So this is trying to make that effect. On the large scale, right? In BRDF, there is the geometry term that in the very, very small scale talks about self-shadowing. On the larger scale, on the texture scale, micro-shadowing does this kind of self-shadowing. And in the larger scale, when you have actual meshes with vertices, this shadowing is described by shadow maps. So geometry in BRDF, and then self-shadowing, and then shadow maps. These three together gives you self-shadowing and shadowing detail. Right, so all these informations now is used in a deferred lighting, right? So let's look at them again. This is Shadowmask, Indirect Diffuse, SSAO, Skybox, Environmental Probe, Reflection Probe, SSR Texture. All those are now used in our deferred lighting pass, so our result looks cool. So let's look at how these are built a little bit. So screen space reflection. The first thing we want to say is we use the stencil buffer again. This is our very reflective bowl, and you can see only this is kind of blacker than the other stuff in stencil buffer, and that's the reason is that there is a receive SSR flag, and if this receive SSR flag is not on, we mark on stencil buffer that SSR should not be performed. So all these white pixels is marking on the stencil buffer, hey, I don't need SSR, just don't do it on me. And this board is saying, okay, yeah, I can, please give me SSR, right? So the screen space reflection has 3 basic steps. So step number 1 is in the previous frame, we take the final color rendered and downsample it using Gaussian blur. So we take this from as a copy from the frame buffer, and then we downsample it. The downsampling way is that we need to kind of blur the thing a little bit so that it reflects kind of a rougher. So it's each pixel takes some of its neighbor's value. The second step is when we for each pixel that's not marked with don't receive SSR flag, we shoot a ray from the camera and march reflected ray in depth buffer, and when we hit something, we record its screen space position. So this is the next step, is called tracing, and the final step is reprojection. So depending on the smoothness of the surface, we choose the mid-map level. So like here we generated a mid-map chain, right? If it's a very smooth surface, then it's a crystal clear reflection. In that case, we use the highest mid-map. But if it's a very rough surface, we use a lower resolution mid-map. We will get, after the tracing, we have a screen space position. We just find out what the color of that is at the appropriate mid-map level. Now there is some optimizations that we have tried. There is a high hierarchical Z ray marching that we are doing. So remember last frame, we not only took the depth buffer, we also performed a mid-map chain calculation with that depth buffer. So we are going to use it here. So here is a presentation that's very that I take from Frostbite's 2015 SIGGRAPH. So we are trying. So the bar here is the depth buffer, and we are shooting the camera from the camera a view direction ray, and we reflect it here. This is a reflected ray direction, and we need to know the reflected ray hits where. So we are going. This is the lowest mid-map level, and we are trying to march the next pixel, right? And we haven't hit anything, so maybe actually we are very far away from the surface, so let's increase the mid-map level and keep on marching. We haven't hit anything, so we increase, so we make a lower resolution, right? So we decrease the resolution like this, and then we finally hit something, right? And when we hit something, we start to increase the resolution so that we know for sure where we hit, and eventually we hit our goal. This kind of speeds up the ray marching by a factor of 2 each time we are lucky and not hit anything, right? Yeah. So the next thing we want to look at is how we generated the SSAO. The first step is we downsample it. We are not blurring. So you know, like when we are doing the color mid-map, we use Gaussian blur. In this case, there's no blur. It's very fast. And then for these, like for the biggest resolution with up to the smallest resolution, for each of them, we calculate the ambient occlusion for them. So the reason we are doing this in multi-resolution is so that we increase the range of occlusion detection, decreasing the accuracy as we go down in resolution. So each of them uses the same number of same size of okay, look at here, right? So when we are calculating the AO, what we are doing is shooting a ray from the camera on a neighborhood of the pixel and checking how large these lines are and taking the average. So when we are having a high resolution thing, we are maybe like saying a 10 pixel neighborhood is this big. But here a 10 pixel neighborhood is that big. So we are actually having a very large range but low accuracy. In this case, we have all these data, then we can summarize the long range but inaccurate data with the short range but accurate data. So this is how we generate ambient occlusion, and then we combine them using bilinear upscaling. What does that mean? What we mean it. So this is the actual calculation when we're doing bilinear upsampling. It's summarized as this. There's two things. First, when collecting occlusion from afar, we receive less influence difference in depth value if break. So we receive less influence if the difference in depth value is big. If the so in the low resolution, you have some depth value and you're trying to upscale to here. And if the depth here and that hit there is similar, it means that this is a helpful information. Then we have a strong influence from this guy. But if we are looking at here's this influence to this place, but the depth change is big, then it's actually not that useful. So we are not going to use it. And finally, this is a multiplication from the high AO with the weighted sum of the low AO. So we accumulate the occlusion from far and from near by multiplying them together. Okay, so let's look at the actual frame. So we're starting with just like before, we're starting with uploading and then clearing buffer, and then we have we need to go flat. So we start with uploading and then clearing the render textures. The first thing we're doing, you can see we're drawing grasses, but in the last frame, the first thing we do is GBuffer Pass, right? But here, the first thing we do is depth prepass for the alpha tested material. So here is the depth prepass as we mentioned. And after we do all the depth prepass, we start to actually do the GBuffer Pass, just like last frame now. And you can see that when we are doing the GBuffer Pass, the depth buffer is already populated with all the grass. So here's our GBuffer Pass, and what is worth noting is in the GBuffer Pass, we not only have color 0, color 1, and color 2 like we saw last time, we also have color 3. This is our Indirect Diffuse. And color 4, this is our Shadowmask. And of course we have depth buffer, stencil buffer, and you can see like the shiny board has a special status in the stencil buffer because only it receives SSR. Now we finished the GBuffer, and then just like last time, we take the depth buffer and generate a mipmap. This will be used later in our screen space reflection calculation. And then we do a SSAO pass. This is a compute shader. Let's look at the events view. Okay. So we are doing downsampling, and then more downsampling, and then we're doing upsampling and occlusion calculation. You can see like all these are the different resolution occlusion depth buffer, and this is the different resolution occlusion texture result. Right, so we are generating all those, and then the next thing we're doing is we are rendering the shadow maps. We're rendering the shadow maps, cascaded shadow like we saw last time. And then we have the tracing step in SSR. This is a big compute shader. And then next is the reprojection step in SSR. So this is the result, right? As you can see in the PowerPoint. Some of the information is missing because so when we shoot the ray from the camera into this ball, this bounces right back into the camera, and there is nothing there, right? We only know about the depth buffer. So screen space reflection only can do so much geometry. And then finally, we do our big deferred lighting calculation. And when we're doing our deferred lighting calculation, we have a lot more to work with. So here is our environmental probe. Here is the ambient SSAO. This is the SSR. We have our diffuse color, normal, F0, indirect diffuse, Shadowmask. Lots of stuff to work with. And just like last time, it's a full screen quad drawing, looping through each light. In our case, there's just one directional light. And then we do a color Gaussian MIP chain. This is getting this color result and downsampling it to make a MIP map. This will be used for SSR next frame. And then we do post-processing. Just like last time we did this is just some exposure calculation to calculate the average brightness of the scene, and then find a blip. So that's it. Okay. This is when we have done the global illuminations, right? And alpha tested texture materials, alpha tested materials. Okay. Frame 3. So now we added transparent object. We have bloom. We have anti-aliasing. We also added, like we enabled transparent object, and here is a transparent object in the scene. To make it transparent, there is a surface type setting in the lit shader. Just choose transparent instead of opaque, then it comes up. Now there is also this fabric shader, which we have made using a very simple shader graph. In HDRP, there is some very complex materials that can only be rendered using forward, and they can only be made using shader graph, not by lit shader. Lit shader is like this guy, right? Now, the transparent material is rendered using forward rendering path, and it just blends on top of opaque images. It's a very standard practice. Complex opaque material, such as fabric and skin, has a lot of surface properties. So if we encode all of them in GBuffer, then we need a very large GBuffer. So in order to, but we can't do it, right? So the solution is to use the forward rendering path instead. So if we look at how it's done, so this is deferred lighting pass, the huge fragment shader over the whole screen. But after that, when we have done illumination for all the deferred materials, the next thing is we draw the forward opaque material. So that's the fabric. And then after that, we draw the sky. So this is the moment when all the opaque is drawn. And then we draw the sky box on only the pixels where we haven't drawn on yet. Right? We use the stencil buffer cleverly here. And finally, we have a forward transparent material being drawn after all the opaque and sky box has been drawn. So we have a deferred forward hybrid architecture in HDRP. Now, there are some special things we need to think about. So when we do this, it introduces some complexities. So let's look at that. Before deferred lighting, we may need output from screen space pre-lighting algorithms such as SSA or SSR. So when we do deferred lighting, the lighting calculation may need some of the occlusion informations that we generate in real time every frame. Now, in order for these screen space pre-lighting algorithms to work, they need to know something about the geometry of the scene in screen space. So this needs to be generated for all the opaque materials in the scene. And therefore, really we need all the normal and depth information about the opaque object brief before SSR, SSAO. So the solution is that forward opaque material also do a pre-pass. And also, if it's a forward opaque material, it not only outputs the depth value, it also outputs the normal value. And the reason for that is when we do SSAO and SSR, we want not only the depth value, but also the normal value. That would enable us to make higher quality calculations in these cases. And although currently we are not using some of them, we will use the normal buffer as well, especially in SSAO. I think we are developing SSAO new algorithm using normal buffer as well as depth. Now, this in picture, right, is this. So when we are doing the depth pre-pass, we not only output to the depth buffer, we also output to the normal buffer. And we have FXAA. That's a very standard thing. It is just a blur of the whole final render result, but also trying to not blur the edges. Vignettes. This makes the edge of the screen darker. It just helps. It looks prettier. And finally, bloom. Right. So bloom, you first downsample and blur, and then you upsample and merge, so that colors from around your fragment influence your fragment. Now, there is a color pyramid generation for SSR, and there is a color pyramid generation for bloom. So we are doing it twice. Some of you might be curious why. Now, bloom has an option called pre-filter, and if you turn it on, then before generating the color map, it does a pre-pass. So the bloom's color pyramid is different from SSR's color pyramid. But we have looked at the code, and in 2019.1 at least, if we turn the bloom pre-filter option off, the color pyramid generation of SSR and blue is quite similar. It's not the same, but it's similar enough. You can look into optimizing them by customizing the code. And the final thing we want to mention is the use of local data share in compute shaders. So this is a map of a compute unit in a GPU. A GPU has a lot of compute units, and each compute unit has a number of threads. And these threads share a branch and message unit. So the instruction each thread runs is very much in sync. And each GPU unit has these many threads. So these many threads can share data with each other through this local data share. And this local data share is a very fast memory access compared to the other memories because it's very close, right? So using local data share caching explicitly in our compute shaders will make it faster. And this is especially useful when we need to find out neighbor values when we are calculating something for a pixel. So what are those cases, right? So there is the color pyramid, there is generation, there is the ambient occlusion, there is the bloom blur, or bloom blur. So bloom, this is color MIP generation, and this is ambient occlusion calculations, and all of those uses the LDS as a cache for the neighboring pixel values, so that we can access neighbor pixel values faster when we have already read it or once before, right? So yeah, this is frame number 3. It's relatively simple, right? So we're just going with the adding some forward shaders and some post-processing. So let's go to the actual thing. So we start with uploading the resources, clearing the textures. Oh wait, uploading resources, clearing the textures, and then we start drawing the grass, right? So this is alpha tester material. We do def pre-pass, but then we also do def pre-pass for the forward material, right? And in this case, we not only draw to the def buffer, but also the normal buffer in case we need those informations in SSR, SSAO, that kind of pre-lighting screen space calculations. Now, then the next thing is the GBuffer Pass. Like last time, we just have the diffuse, color, normal, F0, indirect diffuse color, indirect diffuse lighting, Shadowmask, def, buffer. So you have 3, right? Because we have 4 balls, and one of them is transparent. So transparent doesn't draw to the def buffer. And the stencil, this is special because this guy is the forward ball. Forward shaded stuff also has an extra stencil buffer flag saying, hey, this place is being rendered by a forward shader. Like last time, we copy out the def buffer and make a def pyramid out of it to be used in SSR. We do SSAO like last time. We render the shadow map, the cascade shadow. And then we do the SSR. This is all the same, right? So deferred lighting, this is our huge deferred lighting pass. And after deferred lighting, you can see that it's like this. Now, after deferred lighting, we draw the forward opaque. So that's our silky cloth texture. And then we do a sky pass. We draw the sky because all the opaque stuff is being drawn already. Now, then we draw the transparent object. Then we make a color map chain. Color map chain that's used for, in this case, SSR is also used for some other stuff as well, but we're not turning those feature on in this frame. Post-processing is a bit more involved now because we added all these. As we know, like post-processing is a Wuber shader. But these are the separate downsampling for bloom. So here we are downsampling for SSR, here we are downsampling for bloom. And here we have the final blit. Yeah, so that's the whole thing being drawn. Okay, finished.
Done?
Yeah.
Okay.
Sorry.
It's okay. 네, 여러분 저희 1시간 반 동안 진행된 세션 들어주시느라 고생 많으셨고요. 저희가 질문 받은 건 있는데 지금 바로 답변을 드리기는 좀 어려울 것 같아서 질문은 저희가 수집을 해서 이메일로 다시 답변을 드릴 수 있도록 할 거고요. 지금 요 앞에 세팅이 저희가 오피스를 이번 달에 이전을 해서 신규 브로드캐스트 룸을 세팅을 했어요. 그래서 저희 오프닝 할 때 좀 보이스가 겹치는 현상이 좀 있었는데 양해 부탁드리고요. 저희 이번 세션 이어서 다음 달에 또 마지막 주 화요일에 본 세션 이어서 남은 거 진행할 예정이라 저희가 또 안내 메일 발송해 드릴 거지만 잊지 마시고 다음 달 웨비나 때 또 뵙도록 하겠고요. 그럼 오늘 감사했습니다. 마치겠습니다. 감사합니다.